Lab 5. So, the purpose of this lab was to familiarize ourselves with Faraday's law and apply the law on a visual model. We observed and analyzed a magnet falling through an aluminum tube. The concepts we used were Faraday's law, which can be seen as the Mill equation, and the magnetic force/field equations. The magnetic force being the bottom equation, the magnetic field equation being the top equation, the Biot-Savart law. Specifically, the magnetic force equation, we used sine theta because the force is only going to be in the y component. That's the only part that we're really analyzing. We also utilized Newton's second and third laws. So in the experiment portion, we used a magnetometer app to determine the north pole of a bar magnet. Then we took measurements on the aluminum foil roll, recording the length, thickness, and radius of the roll. We then dropped the magnet approximately 2 inches from the roll while videoing on a phone. We repeated this step 5 times and then analyzed the video for specific enter and exit times, and then took an average of the overall time the magnet took to enter and exit. Then we generated a model in code. So here's the code. This is the top code is the data that we took from the real aluminum foil tube. And there is the magnet properties. And at the bottom is the same equation that I used for lab 3 for the magnetic field equation, which can be seen all the way up here as the top one. So then we also created a flux equation, which is exactly supposed to mirror the equation also back here being the middle equation, Faraday's law. We also created the force of gravity equation, which is just F equals mg, and calculated the ring current, which is I over R equals V. V equals IR, so then I equals V over R. And then we have the rest of the code right there for the ring and the modeling. Here is an image of the code, the overall graph, and the overall time that it took. And this is at the end of the magnet falling. So the results. Experimentally, we found that it only took 0.818 seconds, while the code took 2 seconds, which creates a percent difference of 85%. So there were plenty of sources of error that could have occurred. For example, I used a tape measure for all of the measurements on the aluminum foil roll, which could not be completely accurate, especially because it was in inches, so I had to convert to meters. The magnet I used was kind of chipped and a little bit broken, which most likely affects the weight and overall property. I didn't have an exact weight for the magnet. So the magnetic dipole moment from lab 3 was most likely wrong. So I asked around and I used the general consensus of what the magnetic dipole moment was. I also did this at home, so it wasn't a controlled lab setting. So the what if questions. What if the resistivity was close to 0? So the induced current would be higher because the current is based off the charge and flux over R, which is proportional to resistivity. The magnet would fall slower because the opposing magnetic force would be greater with the increase in the current. And then what if the holes or slots were cut into the tube? it could potentially look like sporadic rings in slanting, a kind of slant position, which would create a different surface for the flux to go through, but overall it would be the same flux, same amount of flux through that surface. If the holes are really big, then that means less conducting material, which means less material to have induced EMF and induced current, which would most likely cause the magnet to fall faster because there's less magnetic force opposition.